Okay, let's wait one more minute until everybody is here. Okay, let's wait until 2 minutes passed. Okay. Yeah, and I think we can start now. Okay, good afternoon. Welcome to this last fourth lecture of the mini school on the theory of open quantum systems. You probably know me by now. My name is Francesco Petruccione, and I will introduce to you now today's speaker, Dr. Graeme Pleasance from UKZN. Yeah? Graeme will, I think, today address the questions of showing some applications of the theory of Markovian open quantum system that he developed in the three previous lectures. Yeah? And as in the past, Dr. Sinaisky always kindly agrees to moderate the questions. So please make use of the question and answer facilities to ask your questions. And since we are not too many, also raise your hand, and we might be able to give you the right to speak in person. Yeah. Okay. So Graeme, thank you very much for being with us again today. And if you would like to start sharing your screen, you're most than welcome to start with your presentation. So thank you very much.
Okay, let me share my screen.
Yes.
Okay, everything's working fine.
Yeah, absolutely fine. Thank you very much.
Okay. Yeah, so, well, thank you, Francesco, for the introduction. And hi again, everyone. So this will be the fourth and last lecture in the mini school series, An Introduction to Open Quantum Systems. So in last week's lecture, we essentially went through a microscopic derivation of the Markovian quantum master equation. And as Francesco mentioned in today's lecture, what we'll hopefully do is to explore some applications of this master equation. Okay, so let me just flip through this. Okay, so in kind of the spirit of last week's lecture, I wanted to just spend, again, a little bit of time at the beginning of this lecture recapping some of the key points that we discussed last time. So, so in the starting point of last week's lecture is that we started from some generic microscopic model of a system-environment interaction. So by this, I mean, we considered a composite quantum system comprising an open quantum system S, which interacts with some macroscopic environment B, where the total Hamiltonian of this composite system can be is written as follows. And if we transform this total Hamiltonian to the interaction picture, then what we did was we defined the von Neumann equation, which is essentially an equation of motion for the density matrix of our composite system S plus B. And we basically used the von Neumann equation as a starting point to construct a master equation for the reduced density operator rho S of an open system, which is in the celebrated GKSL form. Okay, so yeah, I won't go over too many of the technical details again, but basically the way that we begun to derive this master equation is that we formally integrated the von Neumann equation and then plugged its solution back into the right-hand side of the same equation, and then took the partial trace over the degrees of freedom of the environment, so taking the partial trace over B, and by assuming or making if we assume this relation holds at the bottom, then we basically then what we had was an equation of motion for the reduced density operator rho S, which is independent of the initial state of our system environment. So once we had derived this equation of motion for our reduced density matrix rho S, we then introduced a series of approximations to the dynamics of the open system. So the first approximation that we made was the Born approximation. So the Born approximation assumes that the system and environment are only weakly coupled, such that the density matrix of our composite system can be approximately, will remain approximately uncorrelated at all times. And similarly that or secondly as well, that the environment essentially remains static throughout the time evolution. So in other words, what we're basically doing with the Born approximation is we're neglecting any correlations that build up between the system and environment during the course of their interaction. So after implementing the Born approximation, we wrote the previous equation of motion in this form. And then the second approximation that we made was this so-called Markov approximation. So the idea behind the Markov approximation is that we are neglecting any memory effects which are present in the dynamics of our open system. So to kind of clarify what I mean by memory effects, if you look at this equation of motion that we have, we can see that this is in general in the form of an integral differential equation. So what this implies is that the time evolution of our reduced density matrix at some time t will depend entirely on the history of its time evolution. So what we're doing with the Markov approximation is we're basically replacing, on the right-hand side of this equation, we're replacing rho S evaluated at some previous time with rho S only at time t. So intuitively, what we're saying is, or what we're doing is, we're neglecting any dependence of the state of our, we're neglecting any dependence of the dynamics of our open system at some time t on past times. And so this is the kind of first part of the Markov approximation, is making this replacement. And so when you do this, you basically obtain what's referred to in the literature as the Redfield equation. But this equation is not yet in the form of a Markov, in the form of a, well, it's not in the form of it's not in a GKSL form of master equation. So the second part of the Markov approximation basically involves us extending the limit of, well, we firstly basically make a change of variables. So we replace S in this integrand by t minus S. And then what we do is we extend the limit of integration from the upper limit of integration from t all the way to infinity. And intuitively, this kind of extension on the limit of this integral is only will only be well justified if we assume that the integrand disappears sufficiently fast for times S which are much greater than the characteristic timescale over which terms within this integrand decay. So I'll talk a bit more about that that specifically refers to the reservoir correlation functions, which I'll introduce in a few slides. But this kind of formal extension of the upper limit of this integral to infinity can be made if we we can make this extension using a kind of separation of timescales argument. So namely, what we do is if we define a timescale over which our open system evolves due to its interaction with the environment by tau r, and if we also define a timescale over which the reservoir correlation functions contained within this integrand decay by tau b, then we basically assume that that tau r is much greater than tau b. So, yeah, as I kind of mentioned, this timescale characterizes the evolution of our system due to this interaction with the environment. So this is what's called or referred to as the relaxation timescale. In a sense, it tells us how quickly our system decays due to its interaction with the environment. And this timescale tau b characterizes the decay of the reservoir correlation functions. So essentially, these reservoir correlation functions are contained within this integrand. And what we're assuming is that with this kind of separation of timescales, what we're assuming is that these reservoir correlation functions decay very quickly over any time scale of which the reduced density matrix of our open system appreciably varies. So how does this kind of relate to the extension of the upper limit of this integral to infinity? Well, what we said is that when we extend the limit of this integration, we're basically extending the region of integration, or we're extending this integral over a region in which this integrand is approximately 0 because of the assumption of the fast decay of these correlation functions. So when we make this extension, when we extend the limit of this integral to infinity, what we're assuming is that we're only negligibly changing the value of this integral. Okay, so this is the kind of second part of the Markov approximation. And once you perform both the Born and Markov approximations, we basically end up with an equation of motion for the reduced density matrix of our open system in this form. And notably, this equation of motion is completely independent of the initial preparation of our system environment. So the kind of next approximation that we discussed was the so-called rotating wave approximation. And the way that we kind of introduced this was by first examining the interaction Hamiltonian H of I. So as I kind of mentioned last time, is that in the kind of generic setting, we can always write the interaction Hamiltonian as a linear combination of the tensor product of system operators A and environment operators B. So here I refer to these A alphas as these system interaction terms, and these B as these are just environment operators. And to make the to get to a point in which we can then make the rotating wave approximation, what we first do is we introduce a decomposition of these system interaction terms into the corresponding eigenoperators. So these A omegas. So these eigenoperators are defined in the following way. So just to kind of clarify this definition a bit, what we assume to introduce these eigenoperators is that our open system has or the Hamiltonian of our open system, HS, has a discrete spectrum in that this Hamiltonian represents an open system with a discrete number of energy levels whose eigenenergies are labeled by this epsilon. And what these quantities are is that they're operators which project onto the eigenspace belonging to an energy eigenvalue epsilon. And yeah, so we basically obtain the eigenoperators through this relation, and where these omegas are just scalar values which constrain the sum on the right hand side of this expression. So the reason that we introduce this definition of an eigenoperator is that, well, if you recall, these eigenoperators define the Lindblad operators of our GKSL formal master equation. And the reason that they're called eigenoperators is that using this definition, you can show that they satisfy these eigenoperator relations. So for an operator which satisfies this commutator property, this is said to be an eigenoperator of this open system Hamiltonian H of S. Okay, so I won't go over too many more technical details, but another important property of these eigenoperators is that we can decompose our system interaction term into a sum of these eigenoperators. And so yeah, the reason that the introduction of these eigenoperators is useful is when we consider transforming our interaction Hamiltonian into the interaction picture. So when we transform our interaction Hamiltonian into the interaction picture, what will happen is that this will pick up some time dependence. So straightforwardly, when we make this transformation, both these system and environment operators will pick up some form of time dependence. And when we basically perform the decomposition of our system interaction term into its eigenoperators, what this allows us to do when we make the interaction picture transformation is that it allows us to explicitly extract the time dependence that's generated through this interaction picture transformation in the form of exponential factors. So as I mentioned, these operate when we perform the interaction picture transformation. These operators pick up some time dependence, and what we can show through these eigenoperator relations is that this time dependence can be written explicitly in the form of e to the minus I omega t. So this may seem, well, you may ask, okay, well, why do we want to do this? So as I kind of discussed last time, the reason that this is useful is because it allows us to then make the rotating wave approximation. So, okay, so what we at this point, what we discussed is essentially, or what we did here is we just substituted this, the interaction Hamiltonian in the interaction picture into the right-hand side of this expression. And then what you can do is you can rewrite this, after you make the interaction picture transformation, you can rewrite this equation of motion in the following way. And as I previously talked about these reservoir correlation functions. So these reservoir correlation functions are defined as follows. So they're just the expectation value of operators at the environment evaluated at two different times. So again, to emphasize that this time dependence is generated through an interaction picture transformation. Okay, and these coefficients are basically the one-sided Fourier transform of the reservoir correlation functions. Okay, so the rotating wave approximation. So at this stage, we then made the rotating wave approximation. So if we define a, or if we denote the time scale of the characterizing the intrinsic evolution of our open system by tau s. So in other words, the time scale which defines or a parameter tau s which defines a time scale over which our open system evolves according to the okay, sorry, let me read it in this way. So we're defining tau s as a timescale over which characterizes the evolution of our open system, generated by the open system Hamiltonian H of s. So if we define it, we can kind of note that a typical value of this timescale tau of s will be given by the inverse of the difference of omega primed minus omega in this expression. So so intuitively, the way you can kind of see this is that these omegas, so omega prime and omega, will be proportional to the energy eigenvalues of our open system Hamiltonian H of s. So therefore, you can see that their inverse will characterize the timescale over which our the intrinsic timescale over the intrinsic evolution of our system, i.e. the time evolution that's only generated by the open system Hamiltonian H of s. So in order to make the rotating wave approximation, what we assume is that this timescale tau of s is much smaller than the timescale over which our reduced density matrix rho s varies appreciably due to its interaction with the environment. So the way that we implement this is that if we look at this expression, or the way that we implement this is that when we look at this expression, we can see that when we evolve our open system over some time which is of the order of tau of r, then in the case where omega prime is not equal to omega, then, or I should say the terms for which where omega prime is not equal to omega, we can expect these terms to oscillate very quickly due to this separation of timescales argument. So this tau s is very small, but basically assuming this is very small such that its inverse is going to be very large. So therefore, when we have an exponent with a very large when we have an exponential with a very large value in its exponent, we can expect this to oscillate very quickly. So for terms in this equation of motion where omega does not equal to omega prime, we can expect these terms to essentially average very quickly to zero only over any timescale, or over a timescale during which the state of our open systems over S varies appreciably. So when we make the rotating wave approximation, we basically neglect these fast oscillating terms where omega prime is not equal to omega. So after we implemented the rotating wave approximation, we ended up with a master equation for the reduced density matrix of our open system in the following form. So after we made the Born, Markov, and rotating wave approximations, we end up with a master equation which is in the form of a Markovian master equation. So at this point, it might not appear obvious that this is in the form of a Markovian master equation. So the way that we can kind of write this in a GKSL form is by basically decomposing this one-sided Fourier transform gamma into its real and imaginary parts. So when we did this, when we basically separate this quantity in its real and imaginary parts, we introduce these two new quantities, which we denote gamma and S. And basically these coefficients gamma, or each of these coefficients depend on these two indices alpha and beta. And what one can show is that these gamma coefficients form the elements of a positive semi-definite matrix, and that the coefficients of these S coefficients basically form the elements of a Hermitian matrix. So using this, we can then, or if we basically substitute this decomposition into the previous equation of motion, we can basically write our master equation in the following form, where we define this Lamb shift term, which depends on these S coefficients. So the reason that this is called the Lamb shift is that the interpretation of this term is that what it does is it basically it just renormalizes, due to this commutator property, it just renormalizes the energy at levels of our open system. So it basically just shifts. So the energy levels of our open system are represented from the open system Hamiltonian H of S, and what this does is it basically renormalizes these energy levels by a small amount. And then this second term, this first term is we can see kind of governs a unitary time evolution since it's in the form of a commutator. And the second term basically governs a non-unitary time evolution. So this is what's called the dissipator, since it usually describes dissipation in our open system. And so this dissipator depends on these gamma coefficients. And so specifically the fact that these form the coefficients of a positive semi-definite matrix, of a Hermitian matrix, then basically tell us is that this master equation is in the form of is in GKSL form. So if you recall from previous lectures, when I introduced the dynamical map and then introduced the exponential form of the dynamical map, we basically constructed the most general form of the generator of this map, and we basically showed is that it was of this form, and the conditions for this generator were that this first term, so this operator appearing in this first unitary term was Hermitian, and that the coefficients that appeared in the second term, so these gamma coefficients, were positive or formed the elements of a positive semi-definite matrix. So you can see the fact that in this microscopic derivation, the fact that we can prove that these gammas are positive and that these S coefficients are Hermitian then tell us that we've obtained a master equation in GKSL form. And then based on the association of the GKSL form of the master equation to the dynamical semigroup, this then implies that the dynamics describe, or the dynamics that we can obtain from this master equation describes a quantum Markov process. Okay, so I think this is basically where we finished up last time. So as I kind of mentioned, in what we're going to do for the remaining part of today's lecture is hopefully discuss some applications of the Markovian master equation. So probably one of the most commonly encountered applications of the Markovian master equation is in describing the interaction between matter and an electromagnetic field. So so here, when I say matter, I mean something like the interaction between an atom or a molecule or an ion with some surrounding electromagnetic field. So this type of situation is very commonly encountered in quantum optics. So in this situation, our open quantum system is something, like I said, like an atom or an ion or a molecule, and our environment we're modeling as a quantized electromagnetic field. And the reason that this application is of interest is because the approximations that underpin the derivation of the Markovian master equation tend to be well satisfied for these types of systems. So in a kind of typical quantum optics setting. Okay, so so just to kind of introduce the relevant ingredients. So we basically take the total Hamiltonian. So in this kind of quantum optics situation, the total Hamiltonian of our system, again, is just written in the following way. And as I mentioned, we're assuming that our environment is being modeled as a quantized electromagnetic field. So in this situation, the Hamiltonian of our environment, H of B, can be written in the following way. So to kind of introduce the quantities appearing in this expression, what we're basically assuming is that we have some radiation field which is contained within a box of volume V, and that we can decompose the radiation field within this box into its Fourier modes. And these Fourier modes are labeled according to the wave vector K and polarization lambda. And yeah, so yeah, in this way, what these, so in this expression, this operator B lambda K defines the annihilation operator of our radiation field, and this B dagger defines the creation operator of our radiation field. So just to kind of expand on that a little bit, yeah, so again, this is kind of just drawing from the theory of light matter interactions. So I don't really want to delve too much into this, but basically the energy eigenstates of our environment Hamiltonian are the so-called Fock states of the field. So basically these Fock states label the number of photons which are within each mode of the field, which are labeled according to the wave vector K and polarization lambda. And what these creation, or what these annihilation or the definition of these, or I should say that the annihilation operator B is defined in such a way that when it acts on the Fock states, it basically destroys a photon within with wave vector k and polarization lambda. And conversely, this creation operator is defined such that when it acts in a Fock state, it creates a photon of the same wave vector and polarization. Okay, so this is the Hamiltonian of our radiation field. And at this point, we're not making any particular assumption about our open system. We're only assuming that our open system has a non-zero electric dipole moment, such that when our open system is placed in this electromagnetic field, there will be some interaction between the two. So the Hamiltonian describing the interaction between our open system and our environment, our radiation field B, can be, under the dipole approximation, can be written in the following form, where here this D operator is a dipole operator of our open system, and this E is the electric field vector of the radiation field. Okay, so again, this just kind of draws from theory of light matter interactions, but we can represent this electric field in terms of these creation and annihilation operators in the following way, and where these vectors, so these are the so-called unit polarization vectors, and so yeah, this V parameter is just the quantization volume that I talked about, and I should also mention that these omega k's are basically these omega k's just define this dispersion relation of our field. So basically, it relates the frequency of each mode of the field to the wave vector, and we basically, in the kind of general case, assume a linear dispersion relation, such that omega k will just be proportional to the modulus of k. Okay, and then we have some other constants like h bar is just Planck's constant. Okay, and yeah, so having introduced these kind of ingredients, the starting point, what we want to basically do then is to obtain the kind of general form of the Markovian master equation in this situation where our environment comprises an electromagnetic field, a quantized electromagnetic field, and there's our open system and environment interact via a dipole form of interaction. Okay, so the kind of starting point for this is by defining the eigen operators of our open system. So if you can recall from the earlier part of this lecture, these eigen operators are just defined in the following way. So this is just taking the general definition of the eigen operators of our system, yeah, and applying it to this particular form of interaction Hamiltonian. So here we can see that this dipole vector is an operator which pertains to our open system, and this electric field vector is an operator which pertains only to the environment. So you can see that this interaction Hamiltonian is of this generic form that I talked about, where we can write it as the sum of a linear combination of tensor products of system and environment operators. So if you really want to, you can contain this kind of expression implicitly contains a tensor product between these two. And we can also, if we really want to, we can also expand this, we can expand the scalar product. So if we did that, we would basically just get a sum over each of the, we'll get a sum over the products of each of the components of our, or each of the Cartesian components of our dipole operator and electric field, or dipole vector and electric field vector. Okay, so yeah, so we just define the eigenoperators of our system in the kind of, just using the general formula, and we'll be projecting onto the system interaction term, which in this case is, as I've already mentioned, is this dipole operator. And what we can then show is that when we basically make this transformation to the interaction picture, this interaction Hamiltonian can then, after decomposing the dipole operator into its eigenoperators, write the interaction Hamiltonian in the following way. Okay, so this kind of gives us the starting point for us to write down the Markovian master equation for this example. And at this point, it's worth what we can assume is that that our environment, so our quantized radiation field, is initially in thermal equilibrium at some fixed temperature T. So in this way, the initial state of our environment, rho b, can be written using a Gibbs state, which is just this state here, where this Z is the partition function of our radiation field, and this beta is the inverse temperature. So it's defined as 1 over kBT, where kB is the Boltzmann constant and T is the temperature. And if we really want to, we can substitute this Hamiltonian into this expression to show that it can also be written in, that the initial state of our environment could be written in this form. Okay, so having introduced having decomposed our system interaction terms into its eigenoperators, we can then kind of proceed through some of the steps that we went through in the general microscopic derivation of the Markovian master equation. So if you again recall, is that one of the assumptions that went into the derivation was that that the trace of this commutator, so the trace of the commutator of our interaction Hamiltonian in the interaction picture with the initial state of our environment is 0. So for this application, we can show that this assumption indeed holds based on the fact that the expectation value of our environment operator, so this electric field vector, vanishes. So intuitively, the way that you can see this is because this electric field is linear. It's linear in these. It's linear in creation and annihilation operators. So if you basically substitute in the expression for rho b that I gave in the previous slide, and then perform this trace within a Fock state basis, you can basically show that this is 0. Okay, so so the master equation that we have, or that we obtained after we made the Born-Markov approximations, but before we made the rotating wave approximation, was written in this form. So for this example, we can write the Born-Markov the master equation that we have under the Born-Markov approximation in this form. So just to these kind of just to reiterate that these gamma coefficients are the one-sided Fourier transform of our reservoir correlation functions, and that these AI and AJ are our eigenoperators. So just to also mention that in this expression, this sum, which is taken over I and J, sums over each of the Cartesian components of the dipole operator and the electric field, or the dipole vector and the electric field vector. So we're basically saying that these are 3-dimensional vectors. So we're summing over each of their components in this expression. Since, I mean, I'm not going into the details, but you can basically expand out this explicitly in terms of each of the components of this vector, and then basically show that you obtain a master equation of this form under or an equation of motion for our reduced density matrix, or S, under the Born-Markov approximation. Okay, so so the way that we can then proceed from this point is by noting that, well, okay, this is just as I mentioned, this is the one-sided, this gamma coefficient is the one-sided Fourier transform of our reservoir correlation functions. And in this example, based on this form of interaction Hamiltonian that we have, our reservoir correlation functions are going to be formed out of each of the Cartesian components of our electric field vector. So they can be, our reservoir correlation functions are just written in this form. And we can basically, show that these reservoir correlation functions are time homogeneous. So what that means is that we can show that, okay, so our reservoir correlation function is an expectation value of these two operators evaluated at two different times, t and t minus s. And we can show this, that this is time homogeneous for this example in the sense that this expression can be shown to only depend on this time difference s. So the way that you can show this explicitly is by using the fact that for our initial choice of environment state, so a radiation field which is initially in thermal equilibrium, that the Hamiltonian of our radiation field commutes with rho b. So so considering the fact that this time dependence is generated through an interaction picture transformation, so EI at time t is given by e to the I hbt, EI e to the minus I hbt. So therefore, based on this commutation property, we can basically shuffle around this e to the, we can shuffle around e to the I hbt and e to the minus I hbt in this expression to basically show that the time dependence or the time evolution or the time the dependence on this at the current time t basically vanishes, and it only depends on the time difference. So the reason that this is useful is because it helps us then in evaluating the one-sided Fourier transform. Okay, I should maybe ask at this point if there's any questions or if there's anything that people want me to clarify, or should I just keep going? Okay, I assume that people are okay, then I'll proceed. Okay, so yeah, so okay. So after we make the rotating wave approximation, the equation of motion for our reduced density matrix for S can be, for this example, can be written in this form. And yeah, so then we can proceed to, after we've introduced this rotating wave approximation, we can then proceed to evaluate these one-sided Fourier transforms of our reservoir correlation function. So all I've done here is I just, from the previous slide, all I've done is just substitute in the, well, I've just used the fact that these correlation functions are time homogeneous and then substituted that into this expression. And then recalling the fact that, so on the previous slides, I basically gave an expression for the electric field vector in terms of the creation annihilation operators B and B dagger of our radiation field. So what we can then do to evaluate this expression is just to substitute in each of the Cartesian components of our electric field vectors in terms of these creation annihilation operators. So by doing so, what we then end up with is well, it's just this quantity. So so yeah, so what we have is basically, what we have is that we have the one-sided, yeah, what we have is a one-sided Fourier transform of these, or I should say the one-sided Fourier transform of our correlation function depends on the expectation value of these creation annihilation operators. So so basically terms which are quadratic in B and B dagger. So the way that we can then proceed from this point is by using the fact that, well, based on the assumption that our radiation field, so our environment, is initially in thermal equilibrium, then it can basically be shown that that these expectation values satisfy the following expressions. So yeah, so what happens is that terms in which we have either two annihilation or two creation operators vanish, and terms in which we have both a single creation and a single annihilation operator are non-zero. And these two expectation values depend on this quantity here, this n quantity, and this n quantity is essentially the Planck distribution of our radiation field. So basically, what the Planck distribution tells us is the average number of photons occupying a mode of frequency omega k, and we can see that through this Planck distribution that these expectation values depend explicitly on the temperature of our radiation field through this inverse temperature beta. Okay, so we can basically just we can just substitute these expressions into this one-sided Fourier transform, and considering that the only non-zero, so the only non-vanishing terms depend on these Kronecker deltas, what happens is that these double sums, so sums over k and k prime and lambda prime, basically just reduce to sums over k and lambda. And then at this point, what we can then do is, I won't go over all the kind of technical details of this because I think it would just take too long, but basically what we can then do is we can perform the continuum limit. So what I mean by that is that we can basically replace the sum over a wave vector k by an integral taken throughout a volume in k space. Again, I won't go over the technical details of this because I think it would take too much time. But yeah, so by taking this continuum limit and then exploiting some properties of these unit polarization vectors, what you can end up showing is that this one-sided Fourier transform can be written in the following way. Okay, so just something to note here is that we get that the dependence on I and j only enters in through this Kronecker delta here. And to then reduce this expression further, what we can do is we can note the following formula. So what this formula helps us do is it then helps us separate this one-sided Fourier transform into its real and imaginary parts, which go into the definition of these gamma and S coefficients that I was talking about in the earlier parts of this lecture. So, just to mention, so this PV basically defines the Cauchy principal value of the integral. Okay, so basically just substituting this into the above, what we can show is that these one-sided Fourier transforms essentially just reduce to the following. So basically, we can define. So the only dependence, as I kind of mentioned, the only dependence on these indices I and j, which label each of the Cartesian components of our dipole, or in this case, it was the electric field vector. The only dependence on these indices I and j is through this Kronecker delta, and we have these gamma coefficients. So, or we can see that that these coefficients define a kind of diagonal matrix where these gamma coefficients are, so the real parts of this one-sided Fourier transform are defined in are defined here, and the imaginary parts of this S coefficient is written as follows. So hopefully it's clear, kind of, at least from this point, how you end up basically getting these coefficients gamma and S. Okay, so what we can then do is that, as I did in the kind of the generic microscopic derivation of the Markovian master equation, is that you just substitute these into the equation of motion, such that we can then write the master equation in the GKSL form. So that's essentially what I've done in this slide, is I've just substituted in this expression for the one-sided Fourier transform into the equation of motion, such that we can write it in our master equation in GKSL or Lindblad form. So again, what we have here is we have the appearance of a Lamb shift term. So just to note here is that, well, again, this term has the same interpretation as what I previously discussed, in that it basically it describes a renormalization of the energy levels of our open system due to its coupling to the surrounding electromagnetic field. Yeah, and so this Lambshift term is contained in this first unitary term, and or this unitary, the part that describes the unitary time evolution of our reduced density matrix for S, and then in the second kind of non-unitary term, which is a dissipator, we can basically write this in the following way. So I've basically, to write this expression, you can exploit some properties of this Planck distribution. And so intuitively, our dissipator contains two terms. So this kind of, the first term that's contained in our dissipator describes spontaneous, thermally induced spontaneous emission in our open system, which occurs at a rate defined by this coefficient here. And this second term defines thermally induced absorption thermally induced absorption in our open system, which occurs at these rates. Okay, so I think that's, yeah, I'm not sure how much time we have left. So maybe I think I'll have enough time to talk about the application to a two-level system. Okay, so just to kind of sum up this part, what we've basically done is we have applied the Markovian master equation to describing the interaction between a open quantum system which interacts with a electromagnetic field which is initially in thermal equilibrium, and where these two interact via a dipole form of interaction. Okay, so we can kind of consider a more, in the remaining part of this lecture, what we can do is consider a more specific application of this quantum. So just to also mention is that this master equation that we describe, that we've derived in this situation, so where our environment is a quantized electromagnetic field, is that this is what's called the quantum optical master equation. And so what we can do is we can consider a more specific application as well of the quantum optical master equation to a case where our open quantum system is essentially a two-level atom. So this is quite a commonly encountered application in quantum optics. So just to kind of quickly go over this. So what we can now do is we can, as I said, we can consider the case where our open quantum system is described as a two-level system. So in the sense that what we're saying is that our open quantum system is defined on a Hilbert space which is only spanned by two states, which are which we label as G and E, and these two states represent so G represents the ground state of our two-level system, and E represents the excited state of our two-level system. And since any two-level system is isomorphic to a spin half system, the properties of any two-level system can be characterized in terms of the Pauli operators. So here, so these are just the definitions of the Pauli sigma, or here they're labeled sigma 1, sigma 2, sigma 3, but this is just the Pauli X, Pauli Y, and Pauli Z operators. And these operators are defined are just written in this basis. So the excited and ground states of our two-level system are the eigenstates of the two eigenstates of our Pauli Z operator. And so we can also, so we have the Pauli X, Pauli Y, Pauli Z operators. We can also define the corresponding raising and lowering operators of our open system. So these are defined as sigma plus and sigma minus. So these are interpreted as lowering and raising operators, since when we so if we apply sigma minus to the when we apply sigma minus to E, basically it lowers the energy of our system, or it basically promotes our system into its ground state. And similarly, when we apply sigma plus to G, it basically promotes our system into its excited state. So these lowering and raising, so sigma minus is the lowering operator, sigma plus is the raising operator, and they basically connect the two energy eigenstates of our, or connect the ground and excited states of our system. So we assume that for our two-level system that our open system Hamiltonian is just written in the following way, and this parameter omega naught basically defines the energy separation between the excited and ground states of our system. So the energy separation between the states represented by G and D. And importantly, by noting that the fact that these lowering and raising operators, so these sigma minus and sigma plus, are eigenoperators of our open system Hamiltonian, in the sense that you can show that they satisfy these relations, we can basically tell that for this example, that the lowering and raising operators will define the Lindblad operators of this particular example. So, well, the way that you can kind of formally show this is by noting that in the case, well, in this case, we only have we only have our open system only has two different possible states, and so this dipole operator that I previously introduced will be can basically be written as a 2x2 matrix. And again, this just comes from the theory of kind of light matter interactions, but basically what you can argue is that this matrix D basically only contains off-diagonal elements. So basically its diagonal elements are vanishing. And we can basically define the transition matrix element of the dipole operator according to this or just in this way. And since this dipole operator only contains off-diagonal elements in this basis, then we can infer that it can be written in terms of these Pauli lowering and raising operators. Since both of these operators, when you express this in matrix form, each of these two operators are off-diagonal, i.e. they have vanishing diagonal elements. So basically what you can show is that this dipole operator can be written as a sum of sigma plus sigma minus, and where each of the, well, we also have these coefficients, which are the transition matrix elements of the dipole operator. And so the way that you can then show that these Pauli lowering and raising operators are the only two eigenoperators of our in this example is you can just basically recall the formal definition of these eigenoperators that I introduced previously. So then just considering that our so here we specified the Hamiltonian of our open system. So the projection operators that go in the definition of our eigenoperators will basically be will project onto the eigenspaces belonging to eigenvalue plus omega naught and minus omega naught. And then basically using this, we can then show that just going back to the definition of the eigenoperators and using the fact that the system interaction term is just this dipole operator, which can be written in terms of sigma plus and sigma minus, we can then basically show that there are only two non-vanishing eigenoperators of our system, which are given by which are given as follows. So they're just given, they're just proportional to these lowering and raising operators, and also depend on these the transition matrix elements of this dipole operator. And in the interaction picture, we can then write this our system interaction operator in the following way. So again, this is just exploiting this eigenoperator relation. Okay, I think I'm maybe starting to run out of time, so maybe I can wrap up with this slide, or would people like me to keep going? Sorry, Francesco, you're muted.
You're still muted, Francesco.
It still says that you're muted, Francesco.
Sorry,
Yeah.
sorry, Graeme.
Yeah.
I forgot to switch on the mic. What I wanted to say, Graeme, and I don't want you to put you under any pressure in a public space. In December, we didn't plan any mini school because it will be probably a short month. So that if you would like one more lecture next week, there is absolute no problem. Yeah, we can extend, and if you have more examples that you would like to share, I'm sure you will find interested participants for that. Completely up to you.
Yeah, I would be. Yeah, I'd be happy to do that. If people would.
Okay, fantastic. Then
would be interested. Then yeah.
Thank you very much, Graeme. Then
Yeah.
so that there is no reason to rush through anything. Yeah. So
Okay.
we have a little bit of a safety buffer for next week, and yeah, no, please. So
yeah,
I didn't want to.
Sorry, let me just so
all that end, and then we can ask people for questions.
Yeah. So hopefully at this point it's kind of clear, or at least hopefully people are at least understand more or less what I've been doing. But basically, in this particular example where we're taking our open system to be a two-level system or a two-level atom, after we obtain the only two Lindblad operators, so A omega naught and A minus omega naught, we can then basically just substitute this into the quantum optical master equation that we derived. So when we assumed an open system which interacted with a quantized electromagnetic field. So if we basically just substitute our Lindblad operators into this expression, we can basically write the master equation in this form. So also just to note that in this expression, we have neglected the Lamann's start shift contribution. So the term that was the term that was contained within the or the Hamiltonian that was contained within the term generating the unitary time evolution of the system. And in this expression, what we've also done is dropped the S label on the reduced density matrix of our open system. So here, this is just the density matrix of this is just the reduced density matrix of our two-level system. And so this is maybe a master equation, which some of you who have at least done a little bit of open quantum systems are maybe already familiar with. So what this master equation basically describes is the time evolution that's generated due to the interaction of a two-level system with an electromagnetic field via a dipole type of interaction. And again, just to reiterate this first, so each of these two components define the two, or collectively these two components define the dissipator of our master equation. So the terms which describe the non-unitary evolution. So this first term describes thermally induced spontaneous emission in our two-level system occurring at a rate given by gamma naught n plus 1. And this second term describes thermally induced absorption processes, so the absorption of excitations from the environment, spontaneous absorption of excitations from the environment, occurring at a rate gamma naught n. where this gamma naught is the spontaneous emission rate when our environment is initially at 0 temperature. And we can basically show that gamma naught it depends on these parameters. So this omega naught, again, just is the transition frequency of our, so this omega naught is the parameter determining the energy separation of the energy eigenstates of our two-level system. This is the modulus squared of the dipole matrix element. And this is just C is the speed of light and H bar is the reduced Planck's constant. Okay, so just to finish then, so we basically have thermally induced spontaneous emission and thermally induced spontaneous absorption. So what we can do is we can then define a total transition rate, which is the sum of each of these two components. So we can define a total transition rate gamma, which is just gamma naught n plus 1, which is just this quantity here. And oh yeah, I should also mention that this n is just the Planck distribution evaluated at the transition frequency of our open system. So this is just the Planck distribution evaluated at omega naught. Yeah, so I think that's probably a good place to finish today's lecture then.
Yeah, thank you very much, Graeme. Thank you very much. Ilya, are there any questions, or is there anyone that raised the hand wanting to pose a question?
During the talk, we have a couple of questions which I typed the answers to, because there was just about, some small things. And so far, I do not see any raised arms.
Okay. Maybe let's give 10 seconds to the participants to think about eventual questions.
Yeah, I appreciate that I went over some of the details maybe quite quickly. So if you have any questions about any part of it, then I'm more than happy to try my best to answer.
Yeah, no, thank you very much. Yeah, I think it was a very clear exposition. And yeah, no, and in particular, the fact that we didn't rush too much through the slides, I think it was really very, very welcome. Yeah. Okay, if there seems to be no more question, Graeme. So you probably did a very, very good job at explaining very nicely these introductory examples from quantum optics, essentially. And
yeah, I'll just say that if anybody has any questions, then I'll just put my email. Up
yes,
in case people think.
Yeah. Thank you very much. And also, Graeme, sorry that I put you on the spot with next week. No, thank you very much for offering that, and we will advertise the 5th lecture in the series then by latest tomorrow, because I'm not sure that we will be able to use the same link. I don't know, it's a Zoom technical thing that I have to explore. Yeah, but anyway, we will let you know if the link changes, and we will send you definitely a reminder. Yeah. Okay, so then, Graeme, thank you very much again, and we will see you next week and in the same Zoom at the same time. Yeah. So thank you very much to all the participants as well. And please make a note in your diaries to be with us next week as well. Thank you very much. Bye, Graeme. Bye, Ilya. Thank you. Bye-bye, everyone.
Okay. Thank you.
Thank you. Bye-bye.